Welcome to this module on geodetics and coordinate systems. My name is Martin Sanderson, and I'll be guiding you through this module on geodetics and coordinate systems. In our industry, accurate positioning is not just a technical detail. Whether we're drilling a well, mapping a reservoir, or laying infrastructure, we depend on geodetic principles to describe exactly where things are on the Earth's surface and below it. So let's make a start. Due to length, we will break this module into sections. This will be the first section. By the end of this module, you should have achieved 5 core learning outcomes. First, you'll be able to name the most common map projection model and understand the specific error it introduces. This is critical because all projections carry compromises, and knowing those trade-offs ensures you interpret maps correctly. Second, you'll learn to use latitude, longitude, and depth datums properly. These are the foundations of defining position, whether at the surface or within the crust. Third, we'll cover the differences between the various norths, true north, grid north, and magnetic north, and how to correct magnetic readings so they align with true north. Fourth, you'll practice converting positions between absolute coordinates, like UTM, and relative coordinates, such as those tied to a local wellhead. Finally, you'll be able to explain vertical reference datums, which are essential in understanding elevations, depths, and water levels. As we progress, keep linking each concept to field scenarios. Think of well placement, collision avoidance, and regulatory reporting. Let's begin with some essential geographic terms. Cartography is the science and practice of making maps. It provides a mathematical way to represent a point on the curved surface of the Earth. The key coordinates are longitude and latitude. Longitude lines run from pole to pole, converging at the north and south poles like the segments of an orange. They're measured east and west of the prime meridian, with values running from 0 to 180 degrees. East of Greenwich, we use positive numbers. West, we use negative. Latitude, on the other hand, consists of parallel circles running east-west around the globe. They are equally spaced, with 0 degrees at the equator, increasing up to 90 degrees at the poles. For reference, longitude starts at the prime meridian and latitude starts at the equator. These systems give us a universal framework to specify locations anywhere on Earth. Remember that in oilfield operations, precision matters. Misunderstanding even a fraction of a degree could shift your target by hundreds of meters. These concepts may feel elementary, but they are the bedrock of everything else we'll cover. In the oil and gas industry, accurate positioning is absolutely critical. Imagine needing to understand the relative placement of one well to another. Historically, the industry often relied on local relative coordinate systems, for example, saying a target is 1,200 feet away from the surface location along a certain bearing. While useful for local drilling, this approach becomes limiting when we need to integrate data across larger regions. That's why we've moved to absolute coordinate systems like Cartesian coordinates expressed in UTM. Instead of a relative offset, the absolute system might define the same point as 6,234,345 meters north and 474,628 meters east in Zone 31 North. This shift allows for accurate data exchange across organizations, satisfies government regulatory requirements, and ensures that infrastructure, wellbores, and obstacles like power lines are correctly positioned relative to one another. It's all about integration. When geoscience, drilling, and regulatory teams work together, they must all be speaking the same positional language. Without that, errors compound and risks increase. Now let's consider the Earth itself. The Earth is not a perfect sphere. It's an oblate spheroid, meaning it's slightly flattened at the poles. The polar diameter is about 21 kilometers shorter than the equatorial diameter. This difference may seem small. If the Earth were the size of a billiard ball, you couldn't see the distortion with the naked eye. But for geodesists who model country borders or oil field leases, this 21-kilometer variation introduces significant challenges. Our maps, seismic plots, and drilling schematics are all flat, but the Earth is curved. When we project curved data onto flat maps, we inevitably introduce distortions. The art and science of geodesy is about controlling those distortions so that the maps remain useful. In drilling and production, we depend on precise flat maps and grid systems, but we must always remember that they are approximations of a curved world. The foundation of positioning is the system of latitude and longitude, but because the Earth is not a perfect sphere, we need a mathematical model to approximate its shape. This model is the ellipsoid. An ellipsoid is essentially a best fit, near spherical shape scaled to represent the Earth's surface. Importantly, different ellipsoids provide better fits for different regions. To tie an ellipsoid to the real Earth, we use a geodetic datum. A datum defines the orientation and elevation of the ellipsoid to most closely match mean sea level in a given area. Some datums are local, like Mexico's ITRF 2008, some are regional, like NAD 27 in North America, and some are global, like WGS 84, which is widely used in GPS. Choosing the correct datum is critical. If you pick the wrong one, your coordinates can be off by hundreds or even thousands of meters. This picture is an illustration of all the possible locations that the Texas Capitol Dome could be based on the chosen geodetic datum. For instance, an error of more than 500 meters could result if the Ordnance Survey 1936 datum is chosen instead of the WGS 84 datum. The pictorial assumes the global datum, WGS 84, is at the center of the circle. The picture on the right shows Meade's Ranch Triangulation Station, a fundamental station for the North American datum of 1927 NAD 27. What happens when we use the wrong datum? This slide illustrates the very real risks of choosing the wrong datum. A famous case occurred in the North Sea during the development of the tartan field. The jacket was constructed by a Dutch company using the European datum of 1950, their default, without verifying that it matched the British datum used to survey the field. As a result, the platform was positioned more than 1 kilometre away from where it was intended. The consequences were severe. The first well drilled from the platform was a dry hole, and over half of the well slots were rendered useless. Operators were forced to drill wells from semi-submersible rigs and tie them back sub-sea to the misplaced platform. This error, stemming from something as seemingly small as mismatched datums, cost billions of dollars over the life of the field. The lesson is clear. Coordinate systems and datums are not trivial details. They are fundamental to project success. Always check, confirm, and align datums before executing expensive operations. A single oversight in geodesy can ripple into years of financial and operational loss. Unlike GPS, which can give us instant absolute positioning, surveying in drilling operations is an iterative process. Each new survey is tied back to the previous one, meaning errors can compound if not carefully controlled. To determine a well's position, we record depth, inclination, and azimuth at survey stations, then calculate its three-dimensional path. These coordinates are plotted on vertical and plan views, showing true vertical depth against vertical section and north-south versus east-west displacements. From there, we can project trajectories toward the target. The minimum curvature method is now the industry standard for processing these survey points, as it provides the most accurate interpolation of the well path. The key principle is precision. Because surveys build on each other, the spacing between survey points must be managed carefully. Too far apart, and your accuracy drops. Too close together, and you lose efficiency. Understanding how survey data is collected and processed ensures that well trajectories match geological targets and avoid collisions with other wells. Surveying is the link between planned well designs and their execution in the subsurface. When mapping Earth's curved surface onto flat maps, grid coordinate systems are used. They provide a practical way to express positions in straight-line measurements, essential for engineering and drilling. Different projection methods exist depending on geography and application. Planar projections are simple projecting Earth onto a flat plane, but they're only valid near the poles, where distortion is minimized. The Lambert conformal conic projection is widely used in the continental United States. It projects Earth onto a cone, making it well suited for east-west stretches of land. The Universal Transverse Mercator, or UTM, is the most commonly used system worldwide, particularly in oil and gas. It projects Earth onto a cylinder, minimizing distortion in north-south running zones. Each system introduces some distortion of distance, shape, or area, but the goal is to balance these in ways that make the projection useful for a specific purpose. For drilling and mapping oil fields, UTM has become the standard because of its accuracy across mid-latitudes and its global adoption. Planar projection, also called azimuthal projection, is the simplest method of mapping Earth's surface onto a flat plane. Imagine placing a sheet of paper tangent to the globe at one point, then projecting nearby features onto it. At the very center, distortion is minimal and positions are accurate. However, as you move away from that central point, distortion increases dramatically. This is why planar projections are primarily used for the polar regions, where land masses cluster close to the projection center. Since hydrocarbons are rarely found in commercial quantities at the poles, this method sees limited use in oil and gas. Still, it's important to understand because some global data sets may employ it. The key lesson is that no projection is perfect. Every method introduces compromise. Planar projections give excellent accuracy locally, but they cannot scale to larger regions. Lambert conformal conic projection is another approach, particularly effective for regions that stretch predominantly east-west. Imagine wrapping a cone around Earth, intersecting along standard parallels, and then unrolling it into a flat map. Along these parallels, scale is exact, while distortions increase further away. This makes the Lambert projection especially useful in mapping the continental United States, where east-west dimensions dominate. One key detail is that Lambert projections often use feet rather than meters, which requires vigilance when converting data into international oil field systems that typically use metric units. Another important note, users must specify the correct Lambert zone number, since scale and alignment depend on the standard parallels used. Although not widely used outside North America, it remains important when collaborating with US-based datasets or legacy maps. The lesson here is to always verify projection parameters before integrating data. Even a small mismatch in zone number or units can create errors large enough to compromise well placement or asset mapping. The Lambert projection is precise within its zone of application, but like all projections, it has limits. Here is a concrete example of Lambert conformal conic projection applied to the United States. The standard parallels for mainland US are set at 33 degrees north and 45 degrees north. Within this range, scale distortion is minimal, only around 0.5% to 1%. At the extremes, such as Florida, distortions reach around 2.5%. For land-based operations in the continental US, this level of accuracy is generally acceptable. The key point is that Lambert projections balance distortions, keeping them small over wide east-west regions. However, operators must always verify which parallels are being used and where their area of interest lies relative to them. In practice, if you're operating in Texas, your maps will be highly accurate under the Lambert projection. But if you move further north or south, cumulative distortion could affect pipeline planning, lease boundary definition, or well spacing. This reinforces the importance of understanding the assumptions behind the map projection you are working with. Even within a single country, different states may use slightly different configurations. In oil and gas, precision matters. Being off by a few hundred meters could mean missing a target reservoir or drilling into the wrong lease block. Okay, so as a recap of this section, we have gone through some common map projections and saw how each introduces controlled distortion. You should now be able to identify which projection is in use and what errors it introduces. In the next section, we will introduce the most common projection used in the oil industry, which is the Universal Transverse Mercator UTM system. Second, you'll learn to use latitude, longitude, and depth datums properly. These are the foundations of defining position, whether at the surface or within the crust. Third, we'll cover the differences between the various norths, true north, grid north, and magnetic north, and how to correct magnetic readings so they align with true north. Fourth, you'll practice converting positions between absolute coordinates, like UTM, and relative coordinates, such as those tied to a local wellhead. Finally, you'll be able to explain vertical reference datums, which are essential in understanding elevations, depths, and water levels. As we progress, keep linking each concept to field scenarios. Think of well placement, collision avoidance, and regulatory reporting. That concludes the first section on geodetics and coordinate systems. Please make sure to progress to the quiz before moving on to the next section. Thank you.